In the last video, we saw the Brayton cycle, the ideal cycle representing gas turbine engines. At the end of that video, a few improvements were mentioned, including regeneration and intercooling. This video will look at the Brayton cycle that is improved by adding these features. As a review of the basic Brayton cycle seen in the last video, this consists of 4 internally reversible processes and with the assumption of steady flow. The first process is isentropic compression in the compressor. The second is constant pressure heat addition, representing the combustion in the combustion chamber. The third is an isentropic expansion through the turbine. And the fourth is a constant pressure heat rejection as the air returns to its initial state. We also derived the efficiency of the basic Brayton cycle, which is given by A to B equals 1 minus 1 over Rp to the K minus 1 over K power, where Rp is P2 over P1, the pressure ratio across the compressor. In this video, we're going to look at a couple variants to this basic Brayton cycle. Some of these include a free power turbine, reheating, intercooling, and regeneration. Starting with the free power turbine, the difference is that there are now 2 turbines instead of just one. In the standard Brayton cycle, the single turbine both drives the compressor and provides power out. In the free power turbine variant, one of the turbines is there to drive the compressor and is called the high pressure HP turbine, while the second turbine, the free power turbine, is the one producing the power. For all intents and purposes, splitting the turbine into 2 does not affect the thermodynamics of the cycle, so unsurprisingly, the thermal efficiency of this variant of the Brayton cycle is exactly the same as the basic version. The second variant we are going to look at is the Brayton cycle with reheating. The basis of this cycle is the fact that the work output is increased by expanding the gas at higher temperatures. This can be accomplished by expanding the gas in stages and reheating the gas between these stages. This should be done without raising the maximum temperature of the cycle or changing the pressure on either side of the turbine. This looks similar to the free power turbine variant, but here we have a reheater between the 2 turbines. So there's an additional heat in Q reheat between the 2 turbines. In general, there could be more than 2 turbines, but we will stick to just 2. This addition increases the power output of the cycle, but it also reduces the thermal efficiency due to more energy being put in. The third variant to be examined is the addition of intercooling to the basic Brayton cycle. The motivation behind this variant is the fact that the work required by the compressor can be decreased by using multi-stage compression, where the gases are cooled between stages, basically the exact opposite of the reheating variant. This again does not change the pressures on either side of the compressor. As the number of stages increases, the compression becomes more and more isothermal, which decreases the work required to compress the gas. Similar to reheating, this has advantages in terms of the energy balance, but actually reduces the thermal efficiency. To make the situation better, reheating and intercooling are always used in conjunction with regeneration. Speaking of regeneration, this is the next variant to be examined. Regeneration uses the fact that the exhaust gases are usually at a much higher temperature than the air leaving the compressor, and this hotter air can heat up the cooler air going into the combustion chamber. Having higher temperature air into the combustion chamber will lead to a lower amount of heat being required by the combustion, in other words, less Q in. A lower amount of energy in then leads to a higher thermal efficiency. Here's a diagram of a gas turbine engine with regeneration, basically the standard setup, but with a heat exchanger between the exhaust gases and the air into the combustion chamber. Now, one thing that should be noted about this diagram is the non-sequential station numbering. 1 goes into the compressor and 2 comes out, while 3 goes into the turbine and 4 comes out. This is the same as the regular Brayton cycle seen previously. However, now that the regenerator is added, we have the station 5 between stations 2 and 3. This numbering system is useful to compare to the previous Brayton cycle since 1, 2, 3, and 4 all line up. However, what is usually done in practice is to have sequential numbering. We will see some examples in class and in the homework where this, instead of being 5, is 3, this, instead of being 3, is 4, and this, instead of being 4, is 5. Be aware of this, especially for some results like the ones we're going to see on the next few slides. Regeneration is only useful if these exhaust gases are actually at a higher temperature than those coming out of the compressor. In other words, if T4 is greater than T2. Again, here be careful of the station numbering system. If sequential numbering is used, it is T5 that should be bigger than T2. If this is not the case, the heat will flow in the opposite direction, leading to lower temperature gases into the combustion chamber, leading to higher energy requirements and lower thermal efficiencies. This is the case with high pressure ratios, so regeneration should not be used in these high pressure ratio cases. The highest temperature in the regenerator is when the air comes out of the turbine, T4. Air going into the combustion chamber will usually leave the regenerator at a lower temperature than this, so T5 will generally be lower than T4. For an ideal regenerator, T5 is equal to T4. The TS diagram for the Brayton cycle with regeneration is shown here. And one more reminder, the stations could also be numbered as such. So this is 3, this is 4, and this is 5, which again makes this a 5, that a 5, that a 3, that a 3, and that a 5. So again, be careful with that. Here is a comparison of the thermal efficiency of the Brayton cycle with regeneration as compared to the basic Brayton cycle seen in the last video. This line here corresponds to the Brayton cycle without regeneration seen last class. These are the thermal efficiency lines with regeneration. As mentioned previously, regeneration is only useful if T4 is greater than T2. This generally happens at lower pressure ratios. So we can see here that at higher pressure ratios, the thermal efficiency with regeneration drops below that of where there is no regeneration, and is therefore not useful. The equation for the thermal efficiency with regeneration is given by 1 minus T1 over T3 times Rp to the power K minus 1 over K. So similar to the basic version, but with an additional factor of T1 over T3. It can be seen that higher efficiencies occur for lower values of this temperature ratio, T1 over T3. The last variant to be analyzed is a combination of the previous 3 variants, so regeneration with both reheating and intercooling. Here's the situation shown here. We have a regenerator, as well as multi-stage compression with intercooling, and multi-stage turbines with reheating. In this situation, the gas leaves the compressor at an even lower temperature due to the intercooling, and leaves the turbine at a higher temperature due to the reheating. This increases what we previously called T4 and decreases what we previously called T2, which makes the regeneration process even more effective. Going through the analysis, we have quite a few steps. Again, we could have more than 2 compressors or turbines, but we will look at the simplest scenario with only 2 of each. So first, the air comes into the first compressor and can be idealized as an isentropic expansion between points 1 and 2. Next, we have the intercooling stage, which is isobaric, constant pressure between 2 and 3. Ideally, this brings the temperature back down to the initial temperature, T1. Then we have another isentropic compression through the second compressor from 3 to 4. The regenerator is then used to increase the temperature of this stream of air. This again happens at a constant pressure, and ideally gets the temperature up to the exhaust temperature, so T5 equals T9. The air then enters the combustion chamber, where we have constant pressure heat addition between 5 and 6. Then we get to the turbines, isentropic expansion through the first turbine between 6 and 7. Then we have reheating at a constant pressure, again bringing the temperature back up to the temperature into the first turbine, so T8 equals T6. Then through the second turbine, another isentropic expansion between 8 and 9. The air then goes through the regenerator on the other side, cooling it down now. And finally, the air is returned to its initial state through constant pressure heat rejection between states 10 and 1. TS diagram for this entire process is shown here, along with the various heats coming in and out. The most efficient scenario would occur when the pressure ratios are the same in each compressor and each turbine. So for the best case, we have P2 over P1 equals P4 over P3 for the compressors, and P6 over P7 equals P8 over P9 for the turbines. If the number of stages is increased, then the most beneficial case is if all the pressure ratios are equal. The more stages there are, the closer this cycle comes to the theoretical limit of the Carnot cycle. However, in practice, these incremental gains are not worth the extra weight or complexity involved in having more compressors and turbines. And of course, this is all theoretical and idealized. In real life, there are irreversibilities, friction, and other energy sapping effects. So that is the improved Brayton cycle. Here is your pre-lecture example for the day, as well as the answer. See you in class later.